Thank you for having me. Today I'm going to be presenting some of the results from my master thesis. Don't get misled by the title. When I agreed with my supervisor, Professor Luciano Rizzolla, on the title, the main work was developing on the code, and then we shifted towards generating images of M87. But how would you say, the weight of the thesis shifted over time towards the imaging of M87. But yes, a lot of time went also into developing a GPU accelerated code. Keep that in mind. Okay, so the talk is gonna be structured into, let's say 4 parts. I want to give you a brief introduction, but most of you are astrophysicists, so you know what you know all of the stuff. So maybe we don't have to be spending too much time there. Then second, this is very important. Actually, I want you to introduce you briefly into the theory of black hole imaging, so you can appreciate what we're doing, because it's a bit frustrating because a lot of different things come together, plasma physics and physics from general relativity and so on, and it's easy to get confused. Thirdly, I want to talk a bit about the code, depending on how much time we have. And then fourthly, the first application of the code. This is the demonstration of the GPU power. We are gonna be looking at a few images and also movies from M87 star, which will be used to compare against 2021 observation of the EHT, who have not been published yet. So the work is still undergoing. Okay. We all know this picture. I don't have to spend too much time here, but just to maybe get it back into our heads, what we're looking at, it is widely agreed upon that galactic centers of radio galaxies, also inactive galaxies, but that's a topic for another day, harbor a supermassive black hole, which is used to explain this phenomena that we see from radio galaxies, right? We have these jets that extend sometimes far beyond the elliptical galaxies, which in of themselves are very large and vast galaxies. Maybe it's also nice to mention that these are objects of interest. This is the universe at its most extreme. And if we are hoping to find new physics, this is one of the places where we want to look at. One last thing, maybe it's not only that we can test the universe in its most extreme scales, but also it's worth mentioning that supermassive black holes, from our current understanding, they shouldn't really exist because of the last parsec problem. With the age of the universe, we can't really explain why they are so massive. So someone is wrong, either the cosmologists, and the universe is, for example, much older than we think it is right now, or the theoretical physicists are missing something in the formation of black holes. But something is up, because these things clearly exist. Or let's say it's widely agreed upon that they exist. Okay, let's move on. It's a little bit of eye candy. Most of you know this, but this is a radio galaxy. It's Hercules R. It's really far away. So in case you're wondering, with the Event Horizon Telescope, why are we not looking at this galaxy? It is even bigger than M87. It's because it's far away, very far away. And if you remember the torus, if we hope to look into the throat of the beast, there's only a small angle at which you can look into the throat of the beast. Because usually we have this dust torus, which can obscure the view. And from a very shallow inclination, we have the jet, which can also obscure the view. So we really, in terms of, if we want to hope to image a black hole, we need to hope for certain properties. It must be big enough, it must be close enough, and it must have a, let's say, friendly inclination for us to be able to look into the throat of the beast. And this is precisely the case with M87. And it is worth mentioning that we are very lucky with M87, because it has all the right properties for us to look into it. What's particularly, so this is visible light images. This is a visible light image from Hubble, already well aged. but still very interesting. And what's interesting here is that the jet from the center here, from the galactic center, has a slightly different color to the rest of the to the rest of the galaxy because, well, a completely different process leads to the emission of light here. That is the synchrotron radiation. And the synchrotron radiation in the jet of M87, by the time of taking this picture, was so strong that we can see it in visible light. And it was also close enough, like in comparison to Hercules R, M87 is much closer, which is probably also very helpful in resolving this jet. Don't want to spend too much time here. One thing maybe that is worth mentioning, Professor Cruz Osorio had great success in analyzing and understanding the accretion flow onto M87, which is at this time basically well understood, or let's say the magnetically arrested disk accretion model is well established to describe accretion onto M87 star, because it is characterized by very strong jets like this. It is characterized by the matter in a disk region accumulating into blobs, which make it close to the black hole, which disrupts slightly the magnetic field in the jet, which then leads to flaring events. And these flaring events, this is a particularly famous flaring event that was captured by Hubble a while ago, HST1. Since then, ALMA has had, for example, ALMA and APEX have made more observations of the jet and were able to reserve more flares. But it is worth mentioning that from the work of Professor Cruz Osorio and also others, it fits very nicely into our observations. So we see these flares, we see these, also the blob forming in the accretion disk. I'm going a bit too far, I'm sorry. What we have here now is we're living in very interesting times because we were able to achieve ridiculously high angular resolution of a radio interferometer to resolve the shadow of a black hole. That's insane. It's as if you try to build a telescope on the surface of Earth and you try to read a letter on the surface of the moon. It's, difficult. It's not going to be sharp, probably. You have to study the letter a bit, but this is insane resolution that we have here. And it fits very nice with our understanding of the magnetically arrested disks because we have a blob of matter forming, which is expected. Yes. Okay, and of course, maybe I don't need to mention, but the shadow is expected. So we have a 70 degrees inclination, we have a disk, and that means that we have a shadow in the center, which is expected from black holes, but we're gonna get there. Okay, so far for the introduction. Black holes are very interesting objects, and we live in a time where we can study these objects in unprecedented details. Now I want to talk a bit about the theory. I'm gonna be, the slides are gonna be very dry, but stay with me because it's gonna be, if you stay with me, we will have a nice understanding in a few minutes, and then it will be much more fun to look at the results from the fourth chapter. Okay, so first of all, we want to we want to understand the radiation from supermassive black holes, and the gravitational pull is about as extreme as it can be. And we know from Einstein's theory of general relativity that light follows curved paths in curved spacetimes. So there's no way around it. We need to track the curvature, the influence of the curvature of spacetime onto the motion of particles and photons. We all know this from our textbooks, but what's really nice is maybe here what I can what you maybe don't know yet is this formulation of the geodesic equation here in equation 3 and 4, which is the lesser known companion of the geodesic equation. You derive this from the Hamiltonian equations. And it has a few very nice properties. For the conservation laws are trivially apparent, if you have any, depending on your choice of coordinates, of course. And you don't have to compute these Christoffel symbols all the time here. You just need the derivative of the metric, which can, especially when you don't have an analytical metric, but let's just say a large table of a numerically computed spacetime from a binary black hole merger simulation, let's say, then this is very helpful. So this is, we pay the price in equation 3 that we have to contract with the inverse metric, but okay. So for ray tracing code, very helpful, the equations 3 and 4. I have written a code. Of course, I'm going to be showing you a lensing image because why not? This is the background image is from the Gaia survey. This is our night sky. It's a nice 8K image. And takes less than a second or something to render this because GPUs. And yeah, there are also other famous examples. For example, the Einstein lensing around really far. Like this is what we saw with Hubble first. Maybe even another telescope first, but Hubble had a few famous pictures of Einstein lenses. Okay, so we have the motion of particles, and now we need to talk about the radiation transport. So, is there some? It made a noise. Yeah. Okay, I'm just going to continue because I think we are short on time. Okay. Okay. So we have to think about we have a black hole, and then the black hole is surrounded by a medium, and in the medium we want to track the motion of the photons, which in this case are just particles with zero mass, and these particles are subject to sinks, sources, and scattering processes, which are in a non-covariant form described by this equation. It is worth mentioning that the scattering is terribly annoying and difficult to compute. In optically thin media, where there's hardly any scattering, you can use Monte Carlo techniques to somehow, solve this. So in case you're wondering, you'd integrate over a solid angle from this intensity with a scattering kernel that can also influence the frequency, which means we have to integrate over this frequency part too. But the contribution from the solid angle is again a contribution from a solid angle. And that is a contribution from a solid angle. You get the idea. This is not nice. This is difficult to compute. Okay. Maybe worth mentioning is that in optically thick media, which is not what we have around supermassive black holes in our simulations at least, the particle picture with this equation is terribly difficult to solve, but the statistical description, which leads us to a formulation in terms of partial differential equations, that is the M1 scheme, for example, for neutrino transport in neutron star mergers, performs extremely well in optically thick regions. And right now it's a challenge to interpolate between the methods that do well in optically thin regions, where the particle picture holds well, and optically thick regions, where a statistical approach holds well. And the intermediate region is just, people are trying. So in our case, we are around a supermassive black hole. So to give you a sense of how dense the accretion disk is, it's about the density of 300 to 400 kilometers above Earth. I was also a bit surprised, but it's not, for us, like we would be able to breathe this if it was air there, but because the density is very low. But if you remember the distances, then there's a lot of material actually around such a supermassive black hole, even at such low densities, because supermassive black holes are very large. So a few pixels are basically the size of the solar system, if we take a picture of M87. Okay. What's important here to mention is we can neglect the scattering because of the low densities and because we're shooting radio images. The scattering processes are this is a big deal, right? So this accelerates the imaging massively. We don't need to do this annoying Monte Carlo stuff. We can just neglect this. And We have a different problem to solve, and that is the covariance. The equations we mentioned previously are not covariant. Thankfully, it was shown plenty of times, but a famous paper from Ziriyunzi, where he briefly showed that by using Liouville's theorem, we can derive covariant coefficients for the radiation transport. Equation 8 is mathematically correct. That's exactly what we want. But now imagine you solve this numerically. Let's say I is already a pretty large number. You have right now no emissivity, and you have, for some reason, really high absorptivity at a certain time step, and you are very greedy with your time step, then all of a sudden you have a negative intensity. And that's bad. So this is mathematically correct, but numerically challenging. It looks harmless, but this is actually really annoying, you guys. So Ziriyunzi came with a very nice formulation, which applies perfectly for reverse ray tracing. So we have our camera plane, and we have initial conditions as we capture the photons, and then we integrate them backwards in time to find out where they came from. And when we're doing this, these two equations fit perfectly because we can track the optical depth backward in time and the contribution along this optical depth. And when optical depth is very high, we can just cut off the integration because at some point it doesn't matter anymore. So this is mathematical well posed and works really well. Well, of course, G is the redshift factor. So along the trajectory, we have depending on our observer and the emitting and the form momentum of the photon, we have to take redshifting into account, which also will influence the brightness distribution in our images later on. But we will get there. Okay, an honorable mention would be tracking the polarization. So far, we haven't talked about polarization, and I can tell it is very helpful. What does helpful mean? No, it is a very powerful method to analyze the behavior of the accreting matter onto supermassive black holes, and our radio observatories can measure this. So sometimes we just have the data even in our hard drives. We just need to analyze it. The difficult thing is when we are integrating along a geodesic, you have to imagine we choose a polarization basis to describe the polarization of the ray, but this polarization basis is then also subject to the parallel transport due to curved spacetime and can change, which is a bit annoying, which means that the covariant formulation is terribly annoying and difficult to get right, and still an ongoing topic. For example, yes, an ongoing topic. And another thing is this what you see here. This is the Müller matrix, and the Müller matrix basically describes. Oh, I'm skipping a few things. Okay, before we can look at this equation, I need to briefly explain to you what the Stokes basis is. Remember when I was talking about polarization of light? Yes, you can have an infinite amount of arbitrary amount of bases to describe the polarization of light. In radio astronomy, it is typical, or it is common to use the Stokes basis. Stokes I is the total intensity, Q is the horizontal and vertical polarization, U is cross polarization, and V is circular polarization. And the sign is how many left or right-handed polarization you have, or whether you have left or right-handed circular polarization, or whether you have horizontal or vertical polarization. This is what the signs would mean in the I, S, Q, U, and V. Okay, and now for all of these four Stokes parameters, this equation here is the non-covariant way to track the influence of the absorptivities in the intensity in Stokes Q, U, and V. And we introduce additional parameters, that is the Faraday rotation. So when you have a magneto-ionic medium and you have a radio wave that is polarized, then it is subject to the magnetic field and the electric fields that it surrounds it, which can influence the orientation. This is called Faraday rotation. And this influence of rotating and absorbing is described by this matrix here, which is commonly referred to as Müller matrix. And this Müller matrix, let's say, it can be very unfriendly numerically. If you, for example, have small absorptivities, infinitesimally small absorptivities, but pretty high rotativities, then you get eigenvalue problems and the equation doesn't behave that nicely. Even if it behaves nicely, remember the difficulties from this equation. Yeah, that applies also here. So even if the matrix behaves nicely, then the equation still is not mathematically easy to solve. Like it's annoying, you know, we have to use refined, maybe even expensive numerical methods to get this right. The Raptor paper 2 gave a detailed introduction to this. And I think some work needs to be done on the mathematical formulation here. But anyways, let's move on. So far, we have a mathematical description on the radiation transport. In this work, by the way, we focus solely on tracking the intensity. So this was just an honorable mention for the polarization. But in the dominant source of electromagnetic emission in interstellar media, especially around supermassive black holes, is synchrotron radiation. And synchrotron radiation basically comes from, you have a particle that moves relativistically fast, and you have a magnetic field, which means that it makes spiral motion. But to be in the spiral motion, it needs to be constantly accelerated into the spiral motion, which which is why we in German also refer to this sort of behavior as Magnetobremsstrahlung. When you accelerate a particle, it emits braking radiation. And if it is subject to a magnetic field, then it is braking radiation from a magnetic field, which is why we call it Magnetobremsstrahlung. To make it even more annoying, they don't just emit any isotropically because we're moving isotropically into all directions. We are moving relativistically fast in this spiral motion, which means that we have this light cone in which it's emitting. There has been some work done. There's a famous approximation called the synchrotron function, in which is showed that even for a single electron, it's basically continuous function. But you can believe me, it's terribly annoying to get this right. Just so you have the right picture, this is the process that produces the radiation that we see, for example, in the jet of M87. Or you remember the picture of Hercules R in the jet. This is the process that makes this, that gives rise to the radiation that we then later on capture. Okay, maybe a small mention, the math is annoying. I don't want to go too much into detail, but in practice, these equations here are difficult because this emission kernel involves also Bessel functions. Yeah, this is a resonance condition. And maybe I can mention this. So you have this spiral motion, and in the classical picture, you want to compute the Fourier transformation of the spiral motion to get the contribution towards a certain frequency of observation along a certain wave vector. So we have a three-dimensional Fourier transformation. But this thing is moving relativistically fast, and the gyro motion approximations don't apply, and then we have to use an expansion in Bessel functions, and this is very difficult. So in practice, we use fitting formulas, and even getting fitting formulas accurately is difficult. So also a topic of research. Okay, you see this F and the dFd gamma. That is the electron distribution function. And this is a very important part of accurately computing synchrotron emission from interstellar media. Because you know, it's one thing I have forgot to mention a few seconds ago. It is electrons. The vast majority of synchrotron radiations comes from electrons because ions are too heavy and thus not fast enough. Okay. The electron distribution function is critical and important for the accurate description of synchrotron radiation. And unfortunately, not so easy for us to grasp. So we know from observations that electron distribution functions in interstellar media, due to their low densities and their strong magnetic fields, are not thermal. And in order to motivate this, I want to briefly mention, you all remember from your statistical mechanics lecture or statistical physics lecture, the famous result of the electron gas, the relativistic electron gas, that is the Maxwell-Yüttner distribution. And one of the key assumptions was no magnetic field, and a differential phase-space volume element contains enough electrons that we are well within the limit of statistical or average, excuse me, we are well within the average limit of statistical mechanics. And then we have a thermal distribution. So you have now three guesses what is different from interstellar media. We have magnetic fields and very low densities, which means just from that we expect it to not be thermally distributed, which is also verified by a lot of observations. Historically, people have introduced power laws because the vast majority of, maybe I can show this picture here. The vast majority of electrons of synchrotron radiation comes from highly relativistic electrons. And in this highly relativistic regime, the Maxwell-Yüttner distribution doesn't really describe it accurately, but remember, it was terribly difficult to generate synchrotron, to compute synchrotron coefficients. So in Rybicki and Leitman, analytical considerations have been done with, let's go back, the power law distribution, which was basically introduced for analytical considerations as far as I understand. Because this is really only the highly relativistic part of the distribution that Maxwell-Yüttner doesn't get right, and the thermal core is not that important, the emission from thermal core. Recently, I think it was in 2006, in a paper from Xiao, a kappa distribution was proposed that is a thermal-like core and a power law tail. And the idea is that hopefully this describes the electron distribution function in interstellar, low collision, highly magnetized plasmas accurately. And now we can see this picture here. This is the Maxwell-Yüttner distribution. And you can see that the high gamma, there's a strong cutoff in the high gamma region, which is not what we see in interstellar media. Then you can see here the power law distribution, which was for analytical considerations introduced back in the days. And today we mostly work with the kappa distribution that's basically just smoothly connects this power law tail to the thermal core, which is right now, which has been successfully used ever since to describe interstellar media, the electron distributions in interstellar media. Okay, so now we have a problem. We describe the turbulent accretion flow onto supermassive black holes with GRMHD simulations, which means that we have the ion density, the bulk velocity in a differentially small volume element of fluid, the pressure, and the Eulerian frame magnetic field accessible to us, and that's it. There's absolutely no information about what the electrons are doing, and if we had information, it would still not be, like in two-fluid simulation, it would still not be the electron distribution function because we are simply not tracking individual particles. Okay, so what can we do about this? Because we have to do something, right? We need to describe a electron distribution function somehow from known GRMHD simulation data. So in practice, what we're doing is we propose a temperature ratio between the electron temperature, this is what we want, and the ion temperature, in this case P for proton, which is known analytically basically known analytically because we also know our equation of state. So this is an analytical result. This electron temperature here is not trivial. It contains a lot of microphysical information, and this basically describes, it puts all of this, all of the interactions of the turbulent flow of each particle in a low collision plasma into one number. So this is so getting this right is one of the points of our research. What can we do? We can try to compute with particle and cell simulations, for example. We take a differentially small volume element somewhere in our space-time, where we have a macroscopical magnetic field flowing through our differentiably small volume element. And from there, we can track, I don't know, 10 to the 12, 10 to the 30, maybe not 10 to the 30, but in the future, in a few decades. 10 to the 30 is a bit much, maybe, but maybe in the future we can do that. Particles, and then we can connect the ion. If we go back, we can compute from this particle and cell simulations the electron distribution function, the electron properties, but we can also compute GRMHD non-variables in our particle and cell simulation. And the idea is to then track the plasma sigma, plasma beta, and hopefully we can come up with a good fit and describe the electron temperature as a fit of these of the plasma properties. In an ideal world, we use everything that we have from our GRMHD simulation to be as accurate as possible to describe this electron temperature ratio. This is not easy. Okay, so here's a few temperature prescription. In early works, for example, in the Buck paper, I think Siri used a constant temperature ratio, which is a very crude approximation, or very, very, very simple approximation, but it was the best what people could do at that time, because the analysis in terms of the plasma physics has simply not been done at that point. The well-established, I think it was in 2016, Monika Moszczybrowska introduced the Arbiter model, which is today well-established in radio imaging of black holes and in the EHT community. And basically what it does is we have observations of jet region, we have observation of disk region, and we, as a function of the plasma, we propose a temperature ratio in high and low beta regions, and then it just interpolates between these regions. And this is again motivated by observations and has been, well, used successfully ever since. A fairly recent result was from Claudio Meringolo, a fellow colleague of us in Frankfurt. And he conducted a large amount of particle and cell simulations with plasma properties as we would expect them in disk regions. What does that mean? Well, it is turbulent. That is the magnetic field flowing through a differentiably small volume element is about the same strength as the magnetic field developed by the particles due to turbulence. And this leads to a lot of magnetic reconnection in this small volume element. And from there, it was possible to fit an electron temperature, which in this case, this is new now. We have no free parameters. This is now what we refer to as self-consistent. Either this works or it doesn't. And if it doesn't work, then we are getting our microphysics wrong. And if it works, we're getting our microphysics right. Okay. It gets even more annoying because so far we have only temperature prescription. And a temperature, we remember, is the mean squared velocity of the particles. But we know that interstellar plasmas are not described by a Maxwell-Yüttner distribution that well, which is a function of a temperature. Instead, we need some sort of description for the W parameter and also the spectral, not the spectral index, but the kappa parameter. And neither of them are the temperature. Remember, the temperature is the mean squared velocity, and the W in the kappa distribution is just the thermal core, which means that this is some sort of temperature for the thermal core, but it's definitely not the temperature of our distribution. Well, and also we need to scratch our heads and rethink what temperature even means in a kappa distribution, because is this even an equilibrium distribution at all? So there's also some debate on that. So what we're doing is we introduce some sort of first order coupling with an electron injection with a free parameter and fit this to observations. It feels a bit sketchy. You're not the only one. Also, to me, it feels a bit sketchy, but this is the best what we could do right now to analyze the coupling between the relationship between this W parameter and the otherwise thermal electron temperature for thermal distribution. Okay. One last mention that we have to do the same thing for the kappa. Okay. Okay. I have developed a code with GPU acceleration. This was necessary because in radio imaging, we have to compute a lot of images. And after the theory part, you may have been motivated that there are a lot of free parameters. And if we have an image library, you imagine like different inclination, different frequencies, different mass, different black hole mass. You know, at some point you have a lot of parameters that you need to cover. And if it takes a while to compute an image, imagine if you have to compute 1,000,000 images, then you know, even if you have a cluster of a lot of CPUs, then they're gonna be running hot. And then everyone else is angry because they can't run their GRMHD simulations because you're doing imaging, right? So this is not nice. I'm sorry for the slide. So now, how much time do we have left?
10 minutes.
10. Oh, okay. Yeah. Okay, let's go briefly over this because it's not that important. It's if you want, we can talk a bit more about the code afterwards if you have questions for that. But I've written a code. I decided for OpenCL because I decided to use OpenCL to realize the GPU acceleration because, well, NVIDIA's CUDA is proprietary. AMD's ROCm is not well supported. It's basically, you know, I don't like it. And there's not a lot of other options out there, really. I had to do a lot of trickery. I had to also, maybe an honorable mention is I had to introduce a few tricks to make the 32-bit floating point support possible, because GPUs perform much better in 32-bit accuracy than in 64-bit accuracy, and there was a bit there were a few tricks that I needed to introduce, but it worked. Okay. I think I can skip the tests. Okay.
And there is one important test.
Yes, there is one important test, and that is one of the important results. We are doing pretty well in terms of accuracy. This is the blue line here, because in comparison to the Boss code, which I was comparing my code to, we are solving the radiation in 5th order and not with an Euler scheme. So this is expected. It's also nothing to brag about, right? 5th order versus 1st order integration scheme. This is, you know, it is what it is. Maybe something or a nice result is the speed up in comparison to the CPUs that we used in this case, Intel Xeon Platinum CPU from 2021. It was difficult to get this plot right because I just realized I need to explain the tolerance parameters. Okay, give me 2 minutes. How this works is the following. You have a Runge-Kutta integrator that solves in 5th order and in 4th order, and you can use the difference to get an approximation on the truncation error of your step. And if you can track the truncation error of your step, you can introduce a tolerance parameter. Because whenever the step is above your tolerance, you omit the step and recompute it with a smaller step size and thus a higher accuracy. Boss has the same, but only in the geodesic equation. And my code has tracks the error in the geodesic equation and the radiation equations. Because different numerical methods, different codes, they're not on the same scale. And this plot is difficult to get right because, you know, I could have just showed you the timings, the render times, and then we would be all super happy and my code is so much faster. But we really want to compare speed and accuracy. it's easy to be faster if your accuracy is terrible, right? So yes, maybe we can study this plot a bit more later because it's a very dense plot. But there's also a few results we need to talk about, and I have some movies prepared. So the first application of the code, the display of GPU power, was generating an image library of M87. And why this is so expensive, I need to motivate in a few seconds for you guys. We can't just shoot one image because the accretion flow is turbulent. So what we really do is we shoot 500 images, and then to compute the average of those 500 images, to average out the turbulence of the accretion flow to get a better comparison between models. At the same time, our observatories are calibrated or gauged to capture a certain amount of flux, which means that we want to scale our units, including the accretion rate, such that we match the flux of our observatories over this period of time, which means we compute 500 images. How close are we to the target flux? Pretty far off. We need to adjust. Then we compute 500 images. Then we adjust accretion rate. We compute 500 images. Then we and you get the point, right? It's not just 500 images for a model. It is possibly 5 to 10 iterations. And now all of a sudden the computational effort becomes really big, because if you want to have an image library of 400 models, and then each model is 500 images, and then you need 10 to 20 iterations for each model to get your model, then you quickly run into computational constraints, even with a large cluster. And on a single computer, you're not going to be doing much with a single CPU anyways. Okay, so much so for the motivation of why we need the GPU acceleration. Here's a little overview on the parameter space that we covered. We have 5 different GRMHD repositories, each one of 500 GRMHD slices from which we compute snapshots for these spins. We have the temperature models from Monica, well-established R beta model, in which we consider an R beta of 40, 80, and 160. In some models, 160 is believed to be a very good fit to observations. And then we also compare the new temperature model from our colleague Claudio Meringolo in Frankfurt. And because, we also have different electron distribution functions. The thermal one is implemented for good measure, but we know that really we want to model kappa distributions. So this is only for comparison, but it's also relatively easy to compute. So it's good practice to implement also a few thermal models. And then here with the kappa distributions, as you can see, we also have these turbulent kappa prescription, which is computed from particle inside simulations of turbulent plasma flow, as we expected in disk regions from Claudio's simulations. And then from an older work, there was a current sheet-like simulation with much less turbulence, but this is also a fit for the kappa coefficient, which we included into our models. So in this case, it was like 400 models, but in practice was well over, I don't know, 500, 600, because the parameter space changed during simulations and so on. Okay. One of the first results is the difference in emission pattern from the temperature prescription, from the well-established temperature prescription R beta, and the new one from our colleague Claudio, where you can see that here we have a more, well, it's almost as if the accretion, it's almost as if the magnetic field lines are the spine, and from the spine we have the emission. And from Claudio's model, it is much more disk dominated, which is also well motivated by observations, actually. This is important because it's important to mention that the front view here is observationally not well motivated for M87. It's basically constrained to be an inclination of 163 degrees or 17 degrees, depending on how you look at it. So this is for the purpose of visualization. Also, the jet glows a bit more in the Arbiter model. This plot is either the most boring plot you've ever seen or the most interesting one, depending on how you look at it. Imagine we can constrain this. Let's just assume we can constrain our observations towards the difference of the current sheet kappa and the turbulent kappa. Imagine this is possible. This would then mean that we constrain the turbulent or current sheet-like flow in the microscales of the plasma around M87. And these scales are not accessible to us at all from observations otherwise. So this is basically a microphysical constraint, which is very nice. I don't want to promise you too much because maybe it's not possible. Humans, I mean, we're humans, so we probably don't see a big difference here. And also maybe there is in the light curves a slight difference, but okay. I think it's a nice mention. This is a comparison between the best bet models, our current best bet models of M87, incorporating the particle in cell temperature prescription and the turbulent kappa, and the old well-established Arbiter model. And in case you're wondering why the non-convoluted image on the left side is already blurred, this is an average over 500 images covering an observation of about 5 years. So the turbulent flows averaged out of the plasma. This gives us a much better comparison between the models. And as you can see in the convolved images, there's a slight dip. Both of them are disk-dominated, but here we get maybe a bit more jet contribution from the jet. If we go back a bit, this is from this part here. See? Yeah. And this also here from the top-down view. Okay. One of the important results, maybe this is not directly for the EHT, so we don't need the entire EHT array. We can capture the light curve, I think, also only with ALMA or APEX. But this is big. This is a really important result because the light curve is barely influenced by the R high parameter. But there's a big difference between the self-consistent particle in cell temperature prescription from Claudio and from the Arbiter model from Monica, which means that if we constrain either of these models, we constrain them for good. This is a very nice lookout for the ongoing analysis. Remember, the 2021 observations of EHT are going to be compared to this and is unpublished at this point. Analysis is still going on. But this very nice outlook on constraining. Okay. Yeah, okay, maybe I can talk a bit about the outlook, but our code is fast and accurate, and I think this is nice. In terms of the constraints that we can hope for, this is, I mean, I mentioned this a few seconds ago. With the light curve, we have a very nice outlook on constraining the new models. And other than that, you know, I'm not going to be lying to you guys. The most interesting results are going to be released in our press release from the 2021 observations. And even if I had results already, I wouldn't be able to show you. Otherwise, I guess that would be illegal. Okay. A few reference, and that's it.
Thank you. Maybe you can explain us.
No, I also have movies.
Yes, yes. Also, I mean, what is the advantage to using GPUs instead of CPUs?
Speed.
You can format different. Sorry.
Okay. So these were the inclination movie that Luciano asked for.
Which being?
Yeah, this is 15/16, so 0.94.
What?
Yeah, the negative ones are still rendering. So the data is already done. I have the slices, but just computing the individuals images to then generate the movie also takes a while. Hmm? No, these different inclinations are actually what Luciano asked for because he wanted to better understand. Okay, let me actually show you something. No, this is not what I want to. Give me a brief second.
This is counter-rotating?
Yes, this is counter-rotating. There, I've lost the overview. Don't I have a movie somewhere where I have on the left side the ordinary and then on the right side the blurred ones?
Yeah,
Yeah, I think.
Let's questions. Please. Questions. I have a lot.
Yeah, here is also the model because I see.
Yes.
The first row is the Claudio model.
Yep, exactly. So it's really difficult to find a name for this because
I think turbulent is the correct one, but David was the first. David is.
In your opinion, what are the main differences between a programming with CUDA or OpenCL? Because for what we have different opinions. So in your opinion, what's the main difference and the advantage of using a OpenCL instead of CUDA?
Okay, first of all, the advantage is hardware support. CUDA is okay. There are compatibility layers by now, which you can run CUDA on non-NVIDIA hardware, but these compatibility layers are, a topic for another day. In general, you can say CUDA is proprietary and only for NVIDIA hardware, which is exactly what they want to sell you their stuff. And OpenCL has a very large range of supported hardware. The difference in coding is, are you familiar with graphics programming? With graphics programming, what is a shader? Pixel shader, what is a vertex shader? Okay, then I need to. Okay, CUDA is a bit like an extension of C++, which allows you to write device code, host code, and mixed code. Device code is code that runs on GPU or other devices from NVIDIA, but mostly GPUs. Host code is code that is supposed to run on your machine, the host. And then there's mixed code, which is supposed to run on both machines if you want to use maximum amount of hardware or something. In OpenCL, it's a bit different. You have kernel code. It's a separate, think of it like a separate source file in which you have a different programming language called OpenCL. There's also OpenCL C++, but OpenCL. And think of it like C, except that it is a few limitations. For example, recursion is not allowed, which I think is a good thing. Recursion, don't do this, you guys. Don't use recursion. And for example, GPUs also have vector registers, which are available in this language. Right, so the one is you have C++ code in which you can also write device code. In OpenCL, you have host code and device code, different source files.
You can have the same folder in C++. But okay, we maybe go deeply into this discussion later. More questions?
I'm curious about your best bet.
Yes.
What have we defined best bet?
Well, this is a guess of what.
You can say something like image we already know that it's
yes.
2008.
Exactly. That's basically a guess from 2018. roughly, electron injection 0.5, sigma cut 3, R beta 160. And with Claudio's, not gonna lie, with Claudio's model, we stepped a bit in the dark because analysis is still ongoing. So I should have put this maybe into parentheses, best bet.
Asking about more physical interpretation, what it means 0.5 and epsilon. Physics, yes. Or speed of the black hole plasma.
Yeah, so the spin is currently best bet believed to be 15/16, so highly spinning black hole. But I've also seen in these pizza plots, depending on what temperature model you assume, all of a sudden, for example, -50. So these pizza plots to me seem a bit, depending on your assumptions, they can vary a lot. So I'm looking forward to show you the pizza plot from our analysis. But
Next time.
Next time, yes. In terms of the physical interpretation, well, I think what's very nice is the disk-dominated emission from, which is what we also have in our emission in the image from. I think I have it. Or let's just talk about this. The emission from M87 in 230 gigahertz is clearly disk-dominated. And we have this clear disk domination in Claudio's temperature prescription. Yeah, if we go back to the plot where there was this one, I think, remember? So what we're comparing here is now not the temperature model from Monica, R beta. In everywhere, I think sigma cut was set to 3 because this is roughly speaking the best bet from 2018 observations. Epsilon was set to 0.5. The electron injection also best bet from 2018, roughly speaking. And this only shows